Look at Tallboy, and the first thing you notice is the size. 12,000 pounds. A huge steel weapon carried beneath a specially prepared Lancaster and intended for targets ordinary bombing could struggle to disable. Yet size hides the clever part. Barnes Wallis did not design Tallboy merely to create a larger explosion on the surface. He wanted the bomb to penetrate deeply before detonating. The destructive force would be released below ground, where foundations, underground works, and the earth surrounding a target could become part of the problem. Decades later, the principle sounds almost obvious. In wartime, it created a vicious delivery challenge. Britain could build an extraordinary bomb and achieve very little if it landed in the wrong field. Tallboy was only half the answer. The other half was 617 Squadron, the Lancaster, the bomb aimer, the training, the accuracy. In June 1944, those elements came together over a railway tunnel at Saumur. Tallboy entered combat for the first time. Months later, an even larger British bomb would fall beside a German railway viaduct. It missed the structure itself. 2 spans still came down. So what exactly had Barnes Wallis built? And why could a near miss produce the result that ordinary bombing had struggled to achieve? Friends, let's reach 1,000 subscribers. There really isn't much left to go. Please subscribe, press the hype button, leave a like, and write a comment. Thank you. Now we continue. The problem facing British planners was straightforward to describe and extraordinarily difficult to solve. Bombs could burn buildings, tear apart railway yards, and wreck exposed structures. Wartime engineering, however, adapted. Important equipment could be moved underground. Roofs could be reinforced. Concrete could become thicker. A vulnerable building could become a hardened site whose entire purpose was to absorb attack and continue functioning. There was another frustration. Surface damage could look devastating without producing the military result that mattered. A crater beside a railway line could be filled. Track could be replaced. Approaches could be repaired. Reconnaissance photographs might show a violently altered landscape, while the underlying target remained recoverable. For certain objectives, British planners faced a much narrower question. How do you attack something designed specifically to survive bombing? Barnes Wallis approached the problem as an engineer. His name was already linked to the specialised weapon used against the Ruhr dams in 1943. Tallboy addressed a different obstacle. Wallis's deep penetration concept changed where the explosive energy would be released. A bomb entering the ground before detonation could create destructive effects beneath the surface. An underground cavity might form. Earth could shift or collapse. Nearby structures could suffer through the ground and foundations supporting them. And the word nearby is important. The familiar image of a bunker buster is wonderfully simple. Bomb, concrete roof, direct impact, explosion inside. Real targets were more complicated. A tunnel depends on the hill around it. A viaduct depends on stable ground and structural supports. An underground installation depends upon more than the concrete visible from above. Wallis was looking beyond the roof. The surrounding ground was no longer merely something beneath the target. It could become part of the attack. That made placement critical. Tallboy was not magic. Drop it too far away, and Britain had created an exceptionally expensive crater. The RAF needed crews capable of placing a 12,000-pound weapon close enough to a selected aiming point for its design to matter. Here, 617 Squadron becomes inseparable from the bomb. The squadron is remembered above all for the dam's raid. Its later story is less familiar. 617 continued to be used against difficult targets and trained for specialized precision work. This was precision in the world of 1944. No satellite navigation, no modern laser guidance. Once released, the bomb followed gravity and the conditions of its delivery. The crew first had to reach the correct target. The bomb aimer had to identify the aiming point. The Lancaster had to be flown at the required height, speed, and course. A small error in the aircraft became distance on the ground. Accuracy was human work, and Tallboy was unforgiving of poor work. Its weight did not compensate for a bad release. Then came June 1944. Allied forces landed in Normandy on June 6th. Securing beaches was only the beginning. The bridgehead had to be supplied, expanded, and defended. German forces, meanwhile, needed routes towards the battle area. Rail communications formed part of that contest. 2 nights after D-Day, 617 Squadron headed for Saumur in the Loire Valley. The target was a railway tunnel. From the air, it offered little of the visual drama associated with a major industrial complex. The entrance was a relatively small feature. Much of the target was hidden. Its protection was built into the landscape. A hill stood above it. According to the Imperial War Museum's account, the purpose of the attack was connected to blocking German movement towards the Normandy battle area. For Tallboy, this would be the first operational test. 22 Lancasters of 617 Squadron took part in the raid on the night of 8th to 9th June 1944. Consider the target from the bomb aimer's position. Somewhere below was a railway tunnel, buried beneath a hillside. Surface bombing could damage track and approaches. A large crater might obstruct movement. Tallboy offered a deeper route. One bomb penetrated the hillside and exploded inside the tunnel. Other impacts damaged the railway and approaches. The tunnel was blocked. Within days of the Normandy landings, Tallboy had been used against precisely the type of protected target that made conventional attack so difficult. It would be easy to turn Saumur into a perfect technological fairy tale. Britain builds bomb works, problem solved. Weapons development is rarely so courteous. Tallboy did not make hardened targets easy. Its effect still depended on the target, the point of impact, the surrounding material, and the quality of the attack. Crews could miss. Weapons could fail to produce the intended result. Some objectives could require further operations. Britain had not replaced the rest of Bomber Command's arsenal. It had created a specialized answer for selected problems. Soon, heavily protected V-weapon installations became part of Tallboy's operational history. These sites could include enormous structures built to withstand ordinary bombing. For such targets, the roof was only one part of the challenge. Foundations and underground sections mattered as well. This produced a strange visual contradiction. A crater beside a hardened structure can look like evidence of failure. The bomb missed. The building is still standing. Move on. Tallboy demanded a more careful question. What happened below the surface? A direct strike and a useful strike were not always identical ideas. The intended effect depended on the target. A railway tunnel beneath a hill presented one problem. A massive concrete installation presented another. A viaduct presented another again. The aiming point had to serve the weapon's purpose. Wallis had developed the bomb. Operational crews still had to understand where to put it. and Wallis was not finished. Tallboy weighed 12,000 pounds. Grand Slam weighed 22,000. At roughly 10 tons, it was the heaviest bomb ever dropped by the Royal Air Force. Its scale created an immediate practical problem. A Lancaster had to be specially prepared to carry it. This is why photographs of Grand Slam are so difficult to ignore. Placed beside men, the bomb dominates the image. It seems less like ordinary aircraft ordnance and more like a piece of industrial machinery waiting to be lifted into the sky. The spectacle, however, can distract from the continuity in Wallis's thinking. Deep penetration, detonation below the surface, destructive effects transmitted through the surrounding ground. Grand Slam pushed the idea to a greater scale. It did not remove the need for precise delivery. On March 14, 1945, Grand Slam was used operationally for the first time. The target was the Bielefeld Railway Viaduct in Germany. The viaduct had resisted earlier attacks. Railway viaducts present bombers with an awkward geometry. They may stretch across the landscape, but the structural points that must be seriously damaged are comparatively limited. A bomb can fall nearby, excavate an impressive crater, and leave the main structure standing. Track damage may be repaired. A railway route may reopen. Bringing down major spans is a different result. Over Bielefeld, the RAF now carried Wallis's 22,000-pound answer. One Grand Slam fell near the viaduct, a near miss. After years of development, specialized aircraft and precision training, those words should sound disappointing. The bomb had not struck the structure squarely. Then, 2 spans came down. The near miss had produced devastating structural damage. And here, Wallis's idea becomes visible. The target was no longer just the masonry seen from an aircraft. The ground supporting it mattered. The relationship between explosion, earth, and structure mattered. Detonation beneath the surface placed explosive force in a different environment from an open-air burst. Ground could move. A cavity could form. Support could be disrupted. The bomb did not need to behave like an enormous hammer, striking the center of a roof on every mission. For selected targets, it could attack the relationship between a structure and the ground around it. This is also where the dramatic version of the Tallboy story needs to be handled carefully. It is tempting to say German engineers simply could not understand what Britain had done. It makes a magnificent title. The evidence checked for this story does not prove that German engineers, as a group, failed to understand the physics of Tallboy or Grand Slam. There is no need to invent officers standing beside craters in disbelief. No fake quotation is required. German engineering had produced heavily protected targets intended to resist air attack. Britain responded with specialized weapons designed to attack selected structures through deep penetration and destructive effects beneath the surface. 617 Squadron then developed the precision needed to make those weapons operationally useful. Engineering answered engineering. Concrete remained formidable. Underground construction remained difficult to attack. Tallboy did not make every bunker helpless. Grand Slam did not make accuracy irrelevant. Wallis had developed another technical option. Britain learned how to use it. That final part deserves more attention than it usually receives. Weapons are easy to remember. Tallboy has a distinctive shape. Grand Slam has astonishing scale. Barnes Wallis has a famous name. Training is harder to turn into an icon. There is no single photograph that captures hours of practice. Accuracy does not sit dramatically on a bomb trolley. Yet, Wallis's deep penetration weapons depended on delivery. Without the crew, Tallboy was a 12,000-pound object falling somewhere in Europe. Without accuracy, Grand Slam could make an extraordinary explosion in the wrong place. The operational weapon was larger than the bomb itself. Lancaster, pilot, navigator, bomb aimer, ground crew, aiming equipment, training, Tallboy or Grand Slam. Every element had to meet over one selected point on the ground. Saumur showed what that combination could do to a buried railway tunnel. Later operations took Tallboy against heavily protected installations. At Bielefeld, Grand Slam's first operational use gave the story its clearest paradox. The bomb missed the visible structure. 2 spans fell. 3 very different target problems, one continuing engineering question. Where should the explosive energy be released? Wallis offered an answer. 617 Squadron faced the next question. Can you put the bomb there? Britain's achievement was in joining the two. That is perhaps the most interesting legacy of Tallboy and Grand Slam. They were not guided weapons in the modern sense. They did not make every fortified target obsolete. Their importance lay in specialization. A particular defensive problem had been identified. A particular weapon was developed. A specialist squadron trained to deliver it. The theory then had to survive contact with real targets. Return to Bielefeld. The enormous bomb has vanished beneath the ground. The Lancaster is already moving away. What remains is the result. A crater beside the target. 2 spans gone. At first glance, the bomb missed. Look at the structure and the ground together, and the story changes. That is the strange lesson hidden inside Britain's largest wartime bombs. Their size attracts the eye. Their weight makes the headline. But raw explosive power was never the whole answer. Design mattered. Placement mattered. Training mattered. Barnes Wallis changed where the attack could take place. 617 Squadron made that idea operational. And at Bielefeld on March 14th, 1945, a near miss did not hide the principle. It revealed it. If this story changed the way you see Tallboy and Grand Slam, tell us in the comments which British wartime engineering story we should investigate next. Radar, Bletchley Park, or another Barnes Wallis invention. Subscribe to Defiant Britain WW2, press the hype button, and help us reach 1,000 subscribers. Thank you for watching.